Hello friends, welcome to our channel. In previous video we discussed about the definition of the non-linear space and examples. In today's video we will discuss some more examples and results based on non-linear space. Theorem: let X be a non-linear space and X, Y belongs to capital X, then modulus of norm of X minus norm of Y is always less than equal to norm of X minus Y, and hence show that the norm is continuous function that is X tends to norm of X is a continuous function of capital X into R. Proof: let capital X be any normed linear space. Suppose X, Y belongs to capital X, then we have norm of X is equal to norm of X minus Y plus Y, which is less than equal to norm of X minus Y plus norm of Y, because A plus B norm is always less than equal to A norm plus B norm. This implies norm of X is less than equal to norm of X minus Y plus norm of Y. This implies norm of X minus norm of Y is less than equal to norm of X minus Y. Put it equation number 1. Again, norm of Y is equal to norm of Y minus X plus X, which is less than equal to norm of Y minus X plus norm of x, which is equal to norm of x minus y plus norm of x, because norm of x minus y is equal to norm of y minus x. This implies norm of y minus norm of x is less than equal to norm of x minus y. This implies minus 1 into norm of x minus norm of y is less than equal to norm of x minus y. Put it equation number 2. From equation 1 and 2, we have modulus of norm of x minus norm of y is less than equal to norm of x minus y for every x y belongs to capital X. Now we have to prove that norm function is a continuous function, that is f of x is equal to norm of x is continuous on capital X, as capital X is normed space. So it is metric space also. Because every normed space is a metric space. So to prove f is continuous, it is sufficient to prove that if xn converging to x, then fxn converges to fx. Let xn converging to x consider fxn minus fx its modulus, which is equal to modulus of xn norm minus x norm, which is less than equal to norm of xn minus norm of x. This implies modulus of fxn minus fx is tends to 0, as xn tends to x, Thus, if xn converging to x, then fxn converging to fx. This implies f is continuous function on capital X. So, norm function is continuous function on x into r, where r is the set of real numbers. Next theorem. Let capital X be any normed linear space and xn yn are the sequences in capital X such that xn converges to x and yn converges to y, then show that xn plus yn converges to x plus y and alpha into xn converges to alpha into x, where alpha is any real number. That is, if X is a normed linear space and X and Yn are the two convergent sequences in the normed linear space X, if Xn converges to X, Yn converges to Y, then their sum Xn plus Yn is also converges to the sum of X and Y. Proof. Let capital X be any normed linear space suppose xn and yn are two sequences in capital X such that xn converging to x and yn converging to y. Consider norm of xn plus yn minus x plus y, which is less than equal to norm of xn minus x plus yn minus y. This implies norm of xn plus yn minus x plus y is less than equal to norm of xn minus x plus norm of yn minus y, which is tends to 0 as xn tends to x and yn tends to y. This implies xn plus yn is tends to x plus y. Again, norm of alpha into xn minus alpha into x is equal to modulus of alpha into norm of xn minus x is tends to 0 as xn tends to x. This implies alpha xn is converging to alpha x. So we can say as the continuity of addition and scalar multiplication next theorem. Let capital X be any normed linear space then a metric D induced by a norm satisfies first D x plus x1 y plus x1 is equal to dxy. Translation: invariant property. Second, d alpha into x alpha into y is equal to alpha into dxy. For every x, y, x1 is belongs to capital X and alpha is any scalar. Proof: let capital X be any normed linear space distance between x plus x1 y plus x1 is equal to norm of x plus x1 minus y plus x1, which is equal to norm of x minus y. x1 is cancelled by x1, which is equal to distance between x and y. For every x, y belongs to capital X, x1 is also belongs to capital X. This property is known as translation invariant property. Second, consider distance between alpha into x, alpha into y, which is equal to norm of alpha x minus alpha y, which is equal to modulus of alpha into norm of x minus y, which is equal to modulus of alpha into distance between x and y. Thus, distance between alpha x into alpha y is equal to modulus of alpha into distance between x and y. For every x, y belongs to capital X and alpha is a scalar. Next example. Prove that R and C are normed linear spaces where R and C are set of real numbers and set of complex numbers respectively. Solution. Let R be the set of real numbers we define norm function on R as norm of x is equal to modulus of x for every x is belongs to R. First, norm of x is equal to modulus of x is always greater than equal to 0 for every x is belongs to R. If norm of x is equal to 0, then modulus of x is also equal to 0. This implies x is equal to 0. Hence, norm of x is equal to 0, then x is equal to 0. Let x is equal to 0, then modulus of x, that is modulus of 0, is equal to 0. This implies norm of x is equal to 0. So, if x is equal to 0, then norm of x is also equal to 0. Thus, norm of x is equal to 0 if and only if x is equal to 0. So, the first property of non-linear space is satisfied. Second, let x, y belongs to capital R. Norm of x plus y is equal to modulus of x plus y, which is less than equal to modulus of x plus modulus of y, which is equal to norm of x plus norm of y. This implies norm of x plus y is less than equal to norm of x plus norm of y. So, triangular inequality property is satisfied. Third, let x, y belongs to capital R. Norm of x plus y is equal to modulus of x plus y, which is equal to modulus of y plus x, which is equal to norm of y plus x. So, symmetric property is also satisfied. Fourth, let x alpha belongs to R. Now, norm of alpha into x is equal to modulus of alpha into x, which is equal to alpha modulus into modulus of x, which is equal to modulus of alpha into norm of x. Thus, R satisfies all the properties of normed linear space. Similarly, C is also a normed linear space with norm function as magnitude function. It is sufficient for today. In the next video, we will discuss the sequences in non-linear spaces and LP spaces and L infinity norm spaces. So keep in touch, watch our videos and subscribe our channel for more and more videos on these topics. Thanks to all. Have a nice day. Bye bye.